All right, so here's where we shift our focus in sequences and series from our sequences, which are our arithmetic sequences and our geometric sequences, to now arithmetic series and geometric series. So that's what comprises our 1.2 and 1.4. Now, the big difference between our sequences to then series is when we talk about adding or adding slash subtracting terms in a given sequence, well, that then transforms it into being a sequence that builds a series. So when we add any given terms in a sequence, we then construct some sort of series. And these things can either be finite or infinite, as we're going to see. In this lesson, we're going to deal with finite series, which give us a sequence of these different formulas we can go off of. And then in 1.5, we'll go into the infinite geometric series, which changes our perspective on it a little bit there. And we want to be definitely paying attention to that big difference there. But for now, we're going to deal with the arithmetic series and geometric series and their introduction. Now, if we took an arithmetic sequence, something that is adding or subtracting by the same amount of terms, something like 7 to 5 to 3 to 1, we see that it's subtracting away 2 each time. Or we even take like the arithmetic or the geometric sequence, I should say, below that, which is taking 2 and then going to 10 and then going to 50 and then to 250. In Remember, the big difference between arithmetic and geometric sequences is in arithmetic sequences, we add or subtract by the same amount. In geometric sequences, we're multiplying or dividing by the same amount. So let's just see how that looks in this first example. So they said, if I have this arithmetic sequence, its arithmetic series is where I add up all the terms. And if there's 4 terms, I say S4, or the sum of the first 4 terms is equal to all 4 terms added together. In geometric sequences, yes, again, we're going to multiply or add or multiply or divide, sorry, to get to that next term. In this situation, we're multiplying everything by 5. When we go from 2 to 10, it's multiplied by 5. 10 to 50, we multiply by 5. And when we calculate the geometric series, or the sum of the first how many terms, just like we did with the arithmetic series, now we're going to do a sum notation where we add the terms together. So this is where the two sides kind of blend towards each other. Is we know that arithmetic and geometric sequences are calculated using slightly different approach, but the series is we're adding those terms that make up the given series, whether it be arithmetic or geometric. All right, now when we look at the following formulas, these are all going to be on your formula sheet, so don't really worry. The biggest thing we need to pull about these is when we first of all talk about the sum or the series of a given arithmetic sequence, what we can do is we can look at these and say, well, we can either resort to this formula here or this formula here. And again, they're both on your formula sheet, but it depends on the information given. So in the first formula, if we're given the first term and the very last term in the sequence, and we want to figure out its terms, or we want to figure out the sum of those terms, then we can use this formula. If we're given the second situation, it's because we don't know the TN term, aka we don't know what this last term is, but we do know what the common difference is between all of those terms. So are we adding or subtracting by a specific number, and we know that number. We would also know term 1, and we'd also know how many terms are in the given sequence, which is the number n. All right, when we shift our focus to geometric, remember geometric means we're going to multiply or divide to get to that next term. But when we calculate their series, or the geometric series, which is the sum of that given sequence, then what we're going to do is we're going to look at it and be like, well, I could either use this formula here or this formula. The one thing we're going to notice is that the 1 and the r's are flipped. So when we go from this one, r is first. When we go to this one, r is second. But it won't really matter what one we use because the signs are going to come out the exact same way. When we go to the formula 4, which is also on your formula sheet, we have a slightly different approach to this, where instead of just having T1, which was in this formula, if we know Tn and T1 and we know the ratio, or we know any piece of these, then we can go down to this formula when we know the common ratio and we know the n term in the first term. If we don't know what the n term is, but we do know what the ratio in term 1 are, we can use either one of these formulas here. So again, these are all in your formula sheet. We can rely on pulling them from there. You don't have to come in memorizing these things. Just know where to apply and when. All right. Now, in example 1, we have a following situation where they just give us some sequences. They say, hey, we're going to add or subtract or do a mixture of those, and then I'm going to give you a sequence that has a bunch of terms in that sequence. Now, in this given situation, they say in the following sums, and depending on what they ask for, they might just say for the entire thing, for a certain amount of terms. The biggest thing we need to determine, and this is what you might want to write a note on the very top, is we need to figure out is the series arithmetic, or is it geometric? So whenever we start a problem, we always want to start with asking ourselves this, because we need to figure out which one it is, because then it steers us towards certain formulas or certain approaches. So very critical. Now, let's do that for the following example here for A, B, C, and D. They ask us to find the sum for the first 24 terms. That's what S24 means. When we see this new notation of S and then the subscript, they're saying, what is the sum of the first 24 terms? Now, we know a couple things based on this example. First and foremost, we know what T1 is. That's right here. We don't know what Tn is because they gave us an infinite sequence, or an infinite series if we want to call it using our new terminology. So if we know that this series just continues on and on and on based on this pattern, well, first of all, we got to figure out arithmetic or geometric. You can do a really simple test. You can either take the two and subtract them, or take the two and divide them. And what I mean by that is the adjacent terms, and then it will tell you if it's geometric or arithmetic based on the result. In this one, I believe it's arithmetic, but we're going to do our test. We're going to take the second term and subtract the first term. So 1/2 minus 1/12, this is going to be equal to 5/12. Then what we're going to do is we're going to repeat that process one more time, and we're going to do the subtraction of the third term minus the middle term, or third minus second. And again, this gives us 5/12. And if we see that we get the same number, this means there's a common ratio, or there's a common number being added between each of these terms, and therefore we would say arithmetic. Now, if it's arithmetic, then what we're going to do is we're going to say, let's make sure, whoops, there we go. I'm going to back this up here. Perfect, arithmetic. All right, now what we want to do is we want to pick out the appropriate formula from our formula sheet. Again, we should be looking at the one that corresponds to arithmetic series, because if we pick the geometric series, then it's going to give us a totally wrong calculation. So I'm going to write this out from the formula sheet. S24, or the sum of the first 24 terms, is equal to the n value, which is 24, divided by 2, big bracket or square bracket, 2 times the first term, which in this situation is 1/12. And then we're going to do plus n minus 1. Well, 24 is n minus 1, which is just the minus 1, times the common ratio, or the d value, of 5/12. We're going to close our bracket and done. Now, if we put this all into our calculator, I mean, you could simplify this if you wanted to, but if you don't want to simplify this and you're like, hey, I can type this all in one step, no problem. We're just going to go the sum of the first 24 terms is equal to, and from our calculator, we should end up getting that this value is 117. So if I continued this series on and on and on for the first 24 terms and put them all together by addition, I would get the number 117. All right, let's go over to B and do a very similar approach to start it. So I flip over to B here, and term to term, I mean, this one might be a little more obvious. If I go from 3 to 1, 1 to -1, that means what I'm doing to get from term to term is I'm subtracting by 2. But let's just do our quick test. So we're going to go the second term minus the first, which is equal to -2. And then what we could do is we could take the third term, which is -1, and minus the second term. This also gives us -2, confirming that this is an arithmetic series. So I'm just going to make sure we write that in just so that we're confident in what we're choosing here. So we see it's arithmetic, great. Now for step number 2, we're going to select the right formula based on the information we're given. One thing I want you to realize here is that we were given the Tn on the back end. This is the last term, T1 being the first term, so that's 3 here. What we first of all need to do is we need to figure out the number of terms in this sequence, because all they told us was, hey, we have a first, a second, a third, and we have some sort of Tn, but we don't actually know how many terms are in this given series. So what I'm going to do here, and if I say sequence, I'm going to immediately correct myself and say series, because we're calculating a sum of a given series here. A sequence is just a collection of terms separated by comma. The series is when we add or subtract. So now what I'm going to do is I'm going to pull this formula. It's one of our arithmetic formulas. Tn is equal to T1 plus n minus 1 times the common difference d. Now, in this situation, we know a couple things here. We know the common difference, we know Tn, we know T1, so we actually have a lot of info. I'm going to go -37, which is Tn, is equal to 3, which is T1, plus the n minus 1, which we don't know, times the common difference of -2. Now, expanding this, I get -37 equals 3 minus 2n plus 2. Well, 3 plus 2 is 5. -37 minus 5 is going to give us -42, which is equal to -2n. And if I divide both sides by the -2, which would be the appropriate step, I'm going to end up getting that there are 21 terms in the given series. Now for this one, once we know our number of terms in the series, to wrap this up, we're just going to go back to our formula sheet and say, well, it's going to be the sum of the first 21 terms, because n equals 21. And the formula I can use for this one is where we have T1 and Tn, because we know the first term and the last term. So I'm going to go n divided by 2, which is 21 divided by 2, multiplied by t1, which is 3, plus the negative 37. So because my room is fairly limited here, I might have to just go a little bit below. Not the best formatting, but totally fine. So we're going to then say that the sum of the first 21 terms is equal to, therefore, we're going to get negative 357. Now, I just want to double check, like, you go back to this and you're like, does that actually make sense that we're getting a negative number? And if you go back to the original series they gave us, it started off with a really low positive number, 3 and 1, but then immediately within the first three terms, we're now in the negatives, and then it would be like negative 20 something, and then like negative 15 something or whatever. Those numbers that are in the teens and the 20s that would be in this negative value, we're just getting more and more negative. And when we add more negatives together, we're going to get a larger negative number. So this should make sense logically. Just like the last one, we were only adding positive numbers, so of course we should have a positive number. And if we didn't get a positive number, we'd be like, something went wrong in that. Maybe we used a different formula. All right, now here's where we shift our focus and potentially go to geometrics. Right away, I mean, we look at this and they're asking for S15. S15 meaning the sum of the first 15 terms in the series. Now what I'm going to do is, when you look number to number, 40 to 20 to 10 to 5, we're clearly seeing that this is not adding or subtracting by the same amount. So without even questioning and doing a test, I'm like, automatically this has to be a geometric series, because otherwise that just wouldn't make sense. We're not adding or subtracting by some common amount. Now, in the process of recognizing it's geometric, we should figure out that common ratio. What is happening, multiply or divide between the terms? In this situation, we take negative 20, which is term 2, and we divide it by 40. This is going to end up giving us that we have a negative 1/2 ratio. Perfect. Okay, so now that we have our common ratio, we can go to our formula sheet and recognize that we have a couple things on this problem. Our T1 is 40. Our Tn is unknown. It's somewhere over here, but it's not really given, right? So, I mean, we can't use a formula that has that value. So what we're going to do is we're going to copy the following formula from our formula sheet. S15 is equal to, in the very front, we put T1. So we could put our 40 here, bracket. In the brackets, we're going to put our common ratio, negative 1/2, raised to the power of that n value, which is 15, minus 1, close the bracket. In the denominator, we're going to take the r value, which is negative 1/2, and subtract 1. Now, again, in your formula sheet, what you could do, or not off your formula sheet, but in your calculator, you could do this all at once. You could simplify things and then put them together. For me, I'm just going to simplify it all at once and give you that the S15, or the sum of the first 15 terms in the geometric series, is equal to 26.667. And it repeats on a little bit, or not repeats, but it continues on a little bit with a couple more decimals. Depending on the accuracy we're looking for, we could round this to a tenth, a hundredth, a thousandth, really doesn't matter. But because it's a sum, I try to hold on to as many decimals as I can, especially when they don't say round to something specific. So if we added up all the terms, does this make sense? Well, if I go from 40 and then I start subtracting, but then I add a little bit back, and then I subtract a little, and then I add a little bit back, yes, it's not going to be greater than 40. And the reason is because we're continuously subtracting, but we're also continuously adding a little bit back. So it won't be 40, but it will be something slightly less. And because this is an infinite geometric series, it will be somewhere about this 26 eventually, when it kind of tapers off and the values start getting low when we subtract and add and subtract and add. And honestly, this value would go on infinitely, but we're good with this. Okay, now let's go to D. And again, we recognize right away, if I go from 5 to 15, 15 to 45, the only way this is humanly possible is if we had a geometric series, because the values aren't increasing by the same amount each time. They're getting multiplied by the same amount, but definitely not added. Now, just to show that that's what's happening, I'm going to write it as geometric first and foremost, just to confirm that. And then secondary, I'm going to do a test. 15 divided by 5, or the adjacent terms, this gives us a multiple of 3. I take 45 and I divide it by 15. And again, we get the value of 3. We see there's a common ratio here. So I'm just going to make sure I arrow over and say, well, my common ratio is 3. Because when I take the terms and I divide them, or the adjacent terms, I get the same value that they're being multiplied by. Now, for step number 2 here, we look at this and we're like, we don't know how many terms there are in this given series. Again, we have a situation where they give us the first 3 and then tell us what the last term is. So this is our Tn right here. This is our T1. If this is T1 and that's Tn, then we're clearly missing how many terms are in this series. So let's take a second to figure that out. Because we know it's geometric, we're going to copy down the following formula. Tn is equal to T1 times the common ratio n minus 1. Now, n is clearly what we're looking for, but we do know what the n term is, which is 10,935. which is equal to t1, which is 5, times the common ratio, which is 3, which we just solved, and then we have n minus 1. Now, from our previous lesson, what we learned is we learned how to use logs to blend this, but there's a prerequisite step right before we do that. We're just going to divide both sides by 5, and when I take that 10,000 number and divide it by 5, I get 2187, which is equal to 3 to the power of n minus 1. Now, using logs, which again, it's a Math 30-1 unit, and we don't really want to go too much into it, but I'll show you how to do logs very simply for our sake. What we're going to do is when we take the log of both sides, we say log of 2187 is equal to log of 3 to the power of n minus 1. Now, the power we have in logs is when we write both sides with logs, we can take the exponent and use it as a coefficient on that log. So I'm going to rewrite this as log of 2187 is equal to, in the front, we have n minus 1 attached to the log 3. Now, clearly, by division, what we would end up doing in this situation is we would divide both sides by the log 3 to then isolate that given n minus 1. So I'm going to go log 3 and log 3. A little bit messy, but I'm going to try and continue that here. Now, off on the side here, or just maybe on the right-hand side with the remaining space we have, I'll try to write the solution here. We're going to write this as log 2187 divided by log 3. It actually gives us a really nice number out of that. It's 7 is equal to n minus 1. Our last term is just to add 1 here, add 1. So we figured out that there is 8 terms in the given series. Now, our final step is the following. Step number 3, we write that the sum of the first 8 terms is equal to, and from our formula sheet, we can copy down the formula that involves the number of terms, the Tn, and involves the term 1 if we wanted to in this situation. So I'm going to copy this down as we write our common difference on the outside, or not our common difference, our common ratio. And just before I do that, I think it might be helpful just to move this over a tad because I don't want to condense it more than I have to. So let's do that. There we go. That should give us a way better outlook on this. And then I'm even just going to arrow up and say that that's where our step went to. Okay, perfect. So the sum of the first 8 terms is equal to the common ratio, which is 3, multiplied by the Tn, which is going to be 10,935, minus T1, which is 5, all divided by the the common ratio minus 1. So again, just to fill in what I've done here, this was our common ratio, this was Tn, this is T1, and then this is going to be our common ratio, just so that you know which formula I'm using here. Now, in our calculators, the sum of the first 8 terms is equal to 16,400. There we go. And just as a logic check, I always like to go back just right at the end and just be like, does this make sense for the terms they're giving? And in this situation, I would say for sure. Because if we're only positive numbers and we're adding up all these positive numbers, to add up a bunch of positive numbers, including when they get to something like 10,000, yeah, for sure, we should be somewhere in that range of about the mid 10,000s. All right, excellent. So now we've seen arithmetic, we've seen geometric series, and we've seen how to calculate them roughly. We're just going to go into more examples like this where they give us slightly different scenarios. So right away, in a problem, if they ever tell you what type of sequence they gave you, or what type of like overall system we have, we want to highlight that. So at the very top, they say this was given an arithmetic sequence. So we have terms from an arithmetic sequence, which means we add or subtract by the same amount to get to the different terms. And then they gave us the following information. We have T1, which is equal to 17, and we have T38, which is equal to 128. Find the sum of the first 53 terms. When they say that S53, the subscript is just saying how many terms do we want to add together. Now, first and foremost, when we're given some sort of arithmetic sequence, if they don't give us the term, the common difference between the different terms, let's take a second to solve that. So we're going to use our previous knowledge or our previous lessons to be like, if I want the common difference, so I'm just going to take a second to write that, common difference. And this is measured by D in the arithmetic sequences. What we're going to do is we're going to take that T38 and equal it to the T1 plus our n, or number of terms, minus 1 times the common difference. Now, they told us T38 is 128. They also told us T1 was equal to 17. We don't know the n, so we're going to leave it as this. Or sorry, we do know the n because we're taking it from 38. So I'm going to go 38 minus 1 times the common difference. Now, when we do this, it's going to be 128 is equal to 17 plus 37d. I'm going to subtract away 17 from both sides. When I subtract away 17 from both sides, I get 111 is equal to 37D. And just like we've done in previous grades, when we see that we want to isolate for a variable, we just simply divide both sides by whatever's multiplied to it. So this is going to give me that we have a common difference of 3. All the terms are added 3 to get to the next one. So if I want to go from 1 to 2, 2 to 3, I just add 3 for every new step I make along the way. Now that I have my common difference, this gives me a lot of power because now I can go to my series formula that we've established and say, well, if I want the sum of the first 53 terms, this is going to be equal to the n, or the number of terms, 53 divided by 2, multiplied to 2 times t1, which is 17, plus, in this second piece, we're going to write it as the n, which is 53 minus 1, times our common difference we just solved for here. Now, if it helps, again, I'm just going to fill in what we have here. So this is our n divided by 2. This is our t1. This is going to be our n minus 1. And then this is our common difference. Because sometimes I like to write in that formula directly off the formula sheet. Other times I just jump right to the numbers because, the more and more you feel comfortable with them, the better. But if it helps, you can even just write that original formula and then start plugging in. Okay, from here, we could again simplify this in our calculator and do a couple steps in here, or we could just say that the sum of the 53 terms is 5,035. There we go. So we end up getting a slightly big number. And again, we would just want to think about this as, well, if 38 terms meant I had 128, and along the way I'm adding these terms all together, then by the time I go from the 38th term to the 53rd term, I'm going to be somewhere in the thousands. So this should make sense that I get a number somewhere in those thousands. And to be about in the mid thousands, that's really good. Like if it started approaching something greater than 10,000, I might be a little concerned, but logically this kind of fits what's happening in this given sequence. All right, now let's go to example 3 on our next page. Example 3 on our next page, again, they give us this really important information right off the top. We have an arithmetic sequence, meaning we're dealing with adding or subtracting by the same amount. Now, there's a bit of a typo in this problem, and it appears here. We have a bit of a cutoff in our notes, and it's S30 is equal to 175. It should be 1755. If you don't see the 1755, just make sure that you change this to having a 5 on the end, or else our numbers are going to be very skewed, or they're not going to be nice numbers for the most part. Now, if we know this is an arithmetic sequence, again, our biggest thing we need to figure out is what is the missing piece of information? In this situation, we don't have a T1. And when we don't have a T1 and we don't have a common difference, it's like both of those things should be huge red flags. So what I'm going to do is right away, step number 1, I'm going to say we want to find T1. Now, in the process of finding T1, we can use our S30 that they gave us and say, well, the sum of the first 30 terms, which is 1755, is equal to, on the formula sheet, we have this nice formula that allows us to solve for T1. It's 30, whoops, there we go, 30, which is the n value, divided by 2, times T1 plus the Tn. Well, in this situation, Tn is T30, which is 102. Awesome. Okay, now from here, I'm just going to expand this out and say, well, 1755 is equal to 15 times the T1 plus 102. We're going to take that one step further. 1755 is equal to 15T1 plus, I don't know if I did this value. Oh, I did. Okay, so 1530 when I multiply 15 times 102. Now what I'm going to do is I'm going to subtract both sides by 1530. So 1530, 1530. This ends up giving me 225 on my left, which is equal to 15T1. And now in order to figure out the first term, simply, let's just divide both sides by 15. Therefore, we get that the first term in this given series is going to be 15. Nice. Okay, pretty good number here. Now, you could circle that, highlight that, whatever you want to do with it if you want to hold on to it, but I think this is decently clear. So we found our T1. We know T30, S30, but we want to figure out S20, right? So in this situation, now I think another important detail would be we need to find that common difference D. And there's actually a pretty simplistic way of doing this now that we have T1 and we have a T30. If we want to figure out the common difference, so find the common difference, which we know is D in this unit, D is equal to Tn minus T1 divided by n minus 1. Essentially what we're doing is just dividing it by the amount of terms, or the difference in those terms divided by the amount of terms that make up the difference in those. So this will give us D is equal to Tn, which we're going to use our T30, which is 102, minus our T1, which is 15, divided by if there was 30 terms in the sequence, or 30 terms until that t30, then we're going to go 30 minus 1. This gives us a common difference in our calculator of 3. So we add by 3 every new term we go to. Now, with these two pieces of ammo in our tool belt, or these two tools in our toolbox, if you want to phrase it that way, we have step 1, step 2. Step 3 is just, let's figure out that sum that they're asking for. So we're figuring out the sum of the first 20 terms. Rather than the first 30 terms, which was 1755, we now want a few less terms, or more particularly 20 less terms. So we're going to go from our formula sheet, n divided by 2, so 20 divided by 2, multiplied by 2 times t1, which is 15, plus the n minus 1, which is 20 minus 1, times that common difference of 3, close our bracket. Now, again, in our formula sheet or on our calculator, we could break this apart as much as we want to. One prerequisite step that I did here before I did the therefore is I said, well, we can make this look like 10, which is 20 divided by 2, times 30 plus our 57, which is the 19 times 3. And then you could do your therefore. So the S20, or the sum of the first 20 terms, is equal to 870. Perfect. Now, just as a logic check, you're like, does this make sense? Yes, because if we get a number that's large, and in that sense, we have our 30th term, which is 102. So we're not at 30 terms, we're only at 20 terms. So there's a lot of room that's between those two. Our first term is 15, they increase by 3. So they don't increase by that much. Within 20 terms, yeah, that would seem like a very logical like sum to get out of this, a sum of a given series. And the fact that we're 10 less numbers being added to this, giving us this, that should be totally fine for us. Awesome. Okay, let's go to our next example here. So in example 4, again, right at the very top, if they give you this information, arithmetic series, it helps you establish what formulas matter, because until you know if it's arithmetic or geometric, you don't know what formulas you really want to lock into. And that might be a hard thing to distinguish in this unit if you didn't automatically highlight that or find that piece of information. So in this situation, we see again, it's arithmetic, meaning we're going to add or subtract by the same amount between terms. Again, in this problem, let's make sure we add this as 1235, put the dot after that because there was a little bit of a cutoff on this specific number here for our sum of our nth term. Now, in this situation, an arithmetic series has the first term as 11, its nth term as 19, and then the sum of those n terms as 1235. Now, to figure this out, actually, we could just look at our formula sheet and be like, what information would we be missing, if anything? Because I know this is arithmetic, what I can do is right away on my formula sheet, go Sn is equal to, and then we can go our n divided by 2 multiplied by our t1 plus tn. Well, fortunately for us, we actually are trying to solve for n, and they gave us Sn, they gave us the Tn, and they also gave us T1. So the only thing we're missing in this situation is the n value, and that's exactly what we're looking for, is how many terms are in this given series. So let's start plugging in the info. This is going to be 1235, which is equal to the n, which we don't know, divided by 2, times the T1, which is 11, plus the 119. Well, if we simplify this a bit, we get 1235, which is equal to n over 2, multiplied by 11 plus 19 is 130. 130 divided by 2, we can simplify this and say this is equal to 130 over 2, which is 65 times n. Now what I'm going to do is just divide both sides by the 65. There we go, 65 and 65. We end up getting that n is equal to 19. So in this given series, this arithmetic series, to get to that sum of 1235, we must take 19 of the terms and add them together for this given arithmetic series to work. Perfect. And if you wanted to add that into your answer there, you could be like, arrow over after you box it and be like, there are 19 terms. Perfect. Just to make it a little bit more clear if you wanted to, but that's totally optional. I would kind of understand if you're talking about n, we're talking about the number in that sequence. But I mean, the more clear you can be, the better for me, and I would appreciate it. All right, so we've done with a lot of arithmetic series, right? And a lot of arithmetic sequences and that type of information. Now what we're going to do is we're going to go to example 5 and 6, where instead of dealing with arithmetic material, we're going to be dealing with geometric material. And again, if you see that right in the top, make sure you highlight it. So we have T1, which is equal to -2. We have T3, which is equal to -72. And the sum of all the terms in the given series is -18,662. how many terms are there in the sequence. Again, if we need to highlight what this means in our notes, when they ask for how many terms, they're just essentially saying, what is the n value? And as soon as we can figure out what n is, perfect. Now, there's one piece of information that seems very glaringly missing in this situation, and it's the common ratio. We have no idea how much they're being multiplied by or divided by to get term to term. Now, the fact that it's going from -2 to -72, that gives me a lot of logic to be like, hey, it's probably being multiplied. So let's just take a second and figure out what this common ratio is. We're going to find our R value. And again, it becomes the R value in geometric rather than the common difference, which is our arithmetic. Okay, so in our pursuit to find the R value, we're going to go Tn, which is equal to T1 times the common ratio n minus 1. Now, I'm going to use the fact that we had the third term and the first term to help us out. T3, which is equal to T1 times R, 3 minus 1. I'm going to start plugging in the information. -72, which is equal to T3, is equal to T1, which is -2, times the common ratio, which we don't know, squared, because 3 minus 1 in the power gives us 2. Now, what we're going to do is we're going to divide both sides by -2. When we divide both sides by -2, we get 36 is equal to R squared. Of course, as soon as we see this from Math 10C, we're like, we got to square root it. Now it's going to give me that the common ratio between all terms is that we multiply everything by 6. Great. So we have our common ratio. Now, the power that this gives us is because we know what our common ratio is, we can now go to our series formula and go, well, step number 2, the sum of the series, which in this situation, we don't know what that n value is equal to, we're going to take our T1 and multiply it to our Rn minus 1, all divided by our R minus 1. And if you're like, where did that formula come from? It's from our geometric side of the formula sheet for our given sequences, or our given series, sorry. So if we want to calculate a geometric series, the formulas look a little different. Now we're going to write this as Sn, or the sum of that given series, is equal to, we actually know what that value is. It's that -18,662, which is equal to T1. They gave us 2 right at the very top. It's -2. The common ratio we just solved for, so it's 6 to the power of n minus 1 divided by 6 minus 1. Now from here, I'm going to go -18,662, which is equal to -2, 6 to the power of n minus 1, all divided by 5. When we see a term in the denominator, let's get rid of that. We're going to multiply both sides by the 5. When we multiply both sides by 5, the number that I get on the left-hand side is -93,310, which is equal to -2 times 6n minus 1. From here, I'm going to divide both sides by the -2 because I don't like that coefficient. When I take that 90,000 divided by 2, I get 46,655, which is equal to 6 to the power of n minus 1. I'm going to add 1 to both sides, and maybe I'll use a slightly different color just because we've kind of overused that red. This is going to give me 46,656, which is equal to 6n. Oh, look at that. We have to go back to our logarithms, which again, I don't really like in this unit. That's the one thing that I've kind of despise about this unit a little bit, is that we don't have a lot of information on how to use logarithms at this point. In Math 3-1, it will become extremely clear, but to us at this point, we kind of need to use just this one skill in this one time in this given unit. So if you recognize that you have an n in the exponent like this, automatically just think, okay, I got to do logs. Now, here's what it looks like. Once you have it as your terms on the left and then just the exponent term on the right, we can write this as log of the term that's on the one side, so 46,656, which is equal to log of 6n as such. And then from here, once we write it like this, I'm going to drop that n to the coefficient of the log. What I mean by that is when we write logs on both sides, I can drop this n to here. So what I'm going to write this as is log of 46,656, which is equal to n times log of 6. And when I write it like this, now I can divide both sides by the log 6 in order to isolate for the given n value. So log 6. And then this is going to put us that when we do this in our calculator, log 46,656 divided by log 6, you can do your log key directly on the main menu. This is going to end up giving us that the n value is 6, or that there is 6 terms in the series. So if you add up the first 6 terms, that will give you your value. You can highlight that and perfect. Our solution is all good to go here. All right, we have one more example, and this one's probably the least straightforward. But once you kind of see the solution, it will definitely make sense to you. We have a bright group of students here. I'm not worried about this tripping you up for the most part. You'll see it one time and be like, I know exactly how to tackle the next. So they want us to determine the common ratio. As soon as they say a ratio, you know that that must mean geometric series. So even if they didn't say, or geometric in general, because it could be a sequence or a series, depending on what part we're in. But if they say ratio, you have to be like, oh, it's geometric right away. And then from here, they give us the following information. There is a partial sum where the first 3 terms add up to this first term. The first 4 terms add up to make negative 105 over 16. And then the first 5 terms add up to make negative 217 over 32. What is the common ratio? Well, here's how we can actually approach this. For step number 1, let's see if we can figure out some specific values in the given sequence or in the given series as individual terms. What I'm going to do this is I'm going to go, well, T4 is equal to, if I take the sum of the first 4 terms and I minus the first 3 in terms of the first 3 added together, that will only leave me with the 4th term remaining. So what I'm going to do is I'm going to take the sum of the first 4 minus the sum of the first 3, and that will just leave me with T4. In this situation, that's equal to negative 105 over 16 minus, in brackets, negative 49 over 8. And if you're like, why did you use brackets? It's just because of the double negative. Now, in our calculator, we're going to figure out that T4, or the 4th term in this given sequence that builds this series, is negative 7 over 16. Excellent. Okay, now we need to do this one more time. We're going to figure out what is the 5th term, or T5, doing a very similar process. We're going to take this and be like, we know that the sum of the first 5 terms minus the sum of the first 4 terms, if I take the first 5 terms and then subtract away the first 4 terms, it only leaves me with that 5th term remaining. So let's do that here. This is going to be equal to, the sum of the first 5 was negative 217 divided by 32, minus, again in brackets because the double negative, 105 over 16, which is the sum of the first 4. When I do this in my calculator, I'm going to get that the 5th term in this given series is negative 7 over 32. And now all that's left to do is, if I want to figure out the ratio, we know if we take any 2 adjacent terms next to each other, or any 2 terms that are directly next to each other in a given sequence, and I divide them, I can figure out what that common ratio is that multiplies, or in this situation, multiplies or divides to get to that term. Now, let's figure out what it is, whether it's multiplication or division based on what the ratio becomes. Step number 2, we're going to take that our common ratio is equal to the term number 5 divided by term number 4. It's always the larger term, or the term that appears more right, over the term that appears more left, which is equal to, in our situation, negative 7 over 32 divided by negative 7 over 16. And I know that writing double fractions like this is a little bit annoying. If you'd rather write it as side by side, which I'll do below here, you could take this as negative 7 over 32 divided by negative 7 over 16. And you could divide this. That's totally fine as well. At the end of the day, we're going to end up figuring out that this common ratio is equal to 1 divided by 2, or it's a half. So every new term I go to along the given sequence that build this series is going to be, I multiply it by a half. And based on the original sums here, that should make sense. We're getting a more fractional number, and the more fractional number we get, the more it must be being multiplied by something that's less than 1. Now, that might be a pretty big stretch in terms of assuming that we could just look at that and see that right away at our level, but it's one way we could think about that here. So that wraps up our lesson on the arithmetic series and the geometric series. You're going to want to make sure you do some practice on these just to make sure you're comfortable with these. Maybe even revisit some of these examples and see if you can resolve them, just so you can do that. And again, your textbook problems are right here. At the end of our lesson 1.5, there's also additional material for you at the back to practice some of these problems as well. So I would go to that to help you out. All right, good luck with your practice.